Okay, this video presents three examples related to inference for a single proportion. One's a confidence interval, two are significant test related. They're pretty straightforward, so we're going to move through them fairly quickly here. The subtleties to pay attention to that I mentioned in the lesson video are look at how P and P hat are used in the conditions check and in the standard deviation or standard error calculation, because it is different for significance tests than it is for confidence intervals. And this lesson goes by special request. I was asked to give a shout out for this lesson. So Alina, Olivia, this lesson's for you. Okay, first one here. Why don't you pause me and read this? Okay, assuming you've done that, you actually should be able to do this work. We've done confidence intervals before, so why don't you take a second and see if you can lay the work out for this. Pause me again. Well, this is a panic exercise because it's a confidence interval. And we're going to find a 95% confidence interval here for the proportion of students who said they've engaged in binge drinking. So you should be doing this. This is a panic problem, so we're estimating P, the proportion of all U.S. students at four-year colleges who are frequent binge drinkers, and we have a definition of that up above. We've defined our variable here, P. Let's check the assumptions. We're going to be a little bit more sophisticated about how we go about things here. There's no random sample stated, so we're not really sure where these 17,000 students came from, so we want to be careful generalizing our results. Probably okay saying we have independent observations as long as there were 170,000 or more folks to choose from. All right, this is going to sound choppy. I got interrupted and I'm not quite sure where I was at and I don't want to start over. So, independent observations, it's reasonable to assume we had 170,000 students to choose from. That's big, but we'll go with that. And then the sampling distribution of p hat's approximately normal. We're checking n times p and n times 1 minus p greater than or equal to 10, but we don't have a p. So we're going to use the best p we have, and in this case, we don't know p, that's why we're doing a confidence interval. So p hat here is equal to 3314 over 17096. So in the check for normality here, we have to use p hat, the best p we have, and that's 0.1938. It's a one proportion z-test. And the work here then is to actually calculate the interval, and you need to show that work. So recall, that's p hat plus or minus z. All one proportion confidence intervals are z intervals. It's 95%. So that's 1.96. And then we have p times 1 minus p over n, the square root of that. But again, we don't have p. So we use the best p we have here, 0.1938 times 0.8062, p times 1 minus p, over sample size 17,096. Now recall, you can do this, whoops, I screwed up here. It's a one proportion z interval. Don't make that mistake. Recall, you can do this on your calculator. You can do a one proportion z interval on your calculator. Don't calculate what you see here by hand. Let your calculator do the work. And you get 18.79 to 19.98. I'm expressing them as percents here just because I prefer the language of percents, but you can do them as decimals, 0.1879 to 0.1998. And then we have a conclusion. We're 95% confident that 18.79% to 19.98% of U.S. students at four-year colleges are frequent binge drinkers. Hey, as a father, that's a frighteningly high number. It's also a very narrow range. Why is that? Well, it's because the sample size is so large. So when we get a big sample, we can be more precise in our estimates. All right, so that's a panic problem, a confidence interval problem. One of the things you'll have to do when you read the problem is not just decide if it's about means or proportions, but also decide if it's a confidence interval or significance test question. All right, second example here. Read this, please. Pause me. All right, I'll assume you've done that. This is an interesting question taken from the medical field here. We had a previous surgery that for a particular kind of blindness had a 30% success rate. And we can assume this happens all the time. A new procedure is developed. We're going to experiment with it and try and decide if it's better than the old treatment. We don't want to move away from a treatment that's at least working for some without being confident it'll work for a higher proportion. So, clue words here: can we justify the claim the new method is better than the old one? Now, it has significance language here, which helps, but justify the claim, that's significance test language. So a significance test, it's not panic, it's phantoms in this case. And I want you to pause me. I bet you, even though this is proportions and you haven't done a proportions problem, I think you can probably work your way through a good chunk of this if you apply the video that sort of gave an overview of how we do significance testing. So why don't you pause me and see if you can do the phantom steps here. Okay, let's assume that happened. P, we're telling a story, right? So let's be clear on what we're doing here. We're not estimating, we're testing, right? Let's be careful with that. It's not a confidence interval, we're not estimating. We're testing P, all right? The proportion of those blinded by a certain disease who will have successful surgery under the new method, right? We're worried about or concerned with the new method here, and we want to know if it's better than the old, so we're testing P, the proportion of successful surgeries related to the new method. The hypotheses here, all right, the null hypothesis is that nothing's changed. P is still 30% success rate. The alternative then obviously is that it's higher than 30%. We're looking for a more successful surgery. We'll check the assumptions, and SRS isn't given here. In fact, that's probably a normal case for something taking place at a hospital or two. We're trying to do this in some situations on the patients who are available. And perhaps it's not set up as an experiment. We're just doing some initial trials here to see if we think we have success. So we don't have an SRS here. We have to be careful generalizing. Until we set up an experiment, it might not be possible to take our results and say this is going to work at any hospital. Independent observations. Well, it says basically we performed 225 operations. It doesn't say they were randomly selected. It doesn't say they came from a bigger population. It does say surgeons at various hospitals performed them. Do we know that we had 2,250 to select from? Not necessarily. We might point that out. Independent observations, not clear. We had multiple surgeries at multiple hospitals. That might tell us there's some independence, but it's not completely clear. So we're going to proceed with caution. We're not trying to trip anybody up here. Then we have the normality check here. Recall what we did for n times p, n times 1 minus p with confidence intervals. We used p hat. We used the best p we have available. Now in a significance test, it's a little bit different. We have a population proportion. It's 0.3. That is actually the best p we have available until proven otherwise. So prior to starting the test, we think the success rate's 30%. So we're going to use, in the test for normality here, we're going to use the best p we have available. So we use 0.3, not p hat in this case. All right, it's called a one proportion z-test, right? And we're doing phantoms here. So we need a test statistic, and we need a p-value. So the test statistic here is z. And it's estimate minus parameters. So our estimate, our p hat here, p hat is equal to 88 over 225. 88 successes in 225 trials, and that's 0.3911. So estimate, 0.3911, minus the null value, minus the parameter, 0.3, divided by standard deviation. P times 1 minus p over n. Use the best p we have. In this case, we have an idea that p is 0.3 times 1 minus that over 225. And if you do that, you get 2.98. You have to show that work. You have to show the proper mechanics, the proper calculation of the test statistic. Right, then we have a p-value, and there is a one proportion z-test on your calculator. It'll kick out the p-value. But we need to know what that is. The p-value here, right, it's a right-tailed test, is the probability of getting p hat greater than or equal to 0.3911. And that's a normal CDF calculation, 0.3911, to something big. Our mean is P, 0.3, and our standard deviation is 0.3 times 0.7 over 225. I'm doing this the hard way. 0.3 times 0.7 over 225, the square root of all that. And sorry, that goes there, obviously, in the normal CDF calculation. So recall, you can do it with the actual data, or you'll see this more often in your book. They're going to do it with the test statistic. So this is a bit more normal. Getting a test statistic, Z, probability of getting Z greater than or equal to 2.98. Also a normal CDF calculation, 2.98, something big, 0 and 1. And if you do all that, you're going to get 0.0014. So that's a very small p-value. That we're surprised by that result. That would indicate significance in our findings. And so we want to conclude that way. Right? So we reject the null since the p-value is so small. P-value 0.014, right? It's much less than the 1% significance level, so we have strong evidence the new procedure has a higher success rate. All right, one last example. You can go back and pause me if you want to read the cartoon. I'm running out of time. Let's give this a quick read. Pause me. So the only difference here is really, I mean, it's still a significance test using one proportion, but we have a two-sided test. So here we're testing P, the proportion of employees at a large restaurant chain who say stress has a negative impact on their personal lives. We've defined our variable P. The null is that it's 75%, that nothing's different from the national average or the national proportion. The question is, are they different? So look for the clue where it's there. We have the word differ, so it's a two-sided test. We're given an SRS. We have independent observations if there's more than 1,000 employees to choose from, and it's N times P. Best P we have available to check for normality. It's a one proportion Z test here. The test statistic is Z equals our observation. We need a P hat. So we had 0.68, 68%. So we've got 0.68 minus 0.75 divided by the square root of P, best P we have, times 1 minus P divided by 100. And if we do that, we get a test statistic of negative 1.616. Then our p-value, in this case, is 2 times the probability of getting a z-score less than or equal to negative 1.616. 2 times because it's a two-sided test. So with normal CDF, we end up finding that to be 2 times 0.053. Which is 0.106. All right, it's a low p-value, but not low enough, so we fail to reject the null due to the relatively high p-value. Again, when you reject the null, you have to reference the p-value. If there's an alpha, you'll reference that. In this case, there's not. The p-value is just too high. We have insufficient evidence to conclude the proportion of employees at the restaurant chain who say stress has a negative impact on their lives is different than the national proportion. So we got the different in there, we got the population proportion in there as well. So that was quick, but it's the same phantom steps, just a slightly different variation on the problem. Now one last thing here, you might also see data presented this way. This is Minitab. This is the exact same problem we went through. You need to get used to reading these. Here are the hypotheses. Notice how it's written. Here's the number of successes and the sample size. From that, we get p hat as 0.68, which is here. Here's a 95% confidence interval. Here's the z value. In this case, that's the test statistic. And here's the p-value. So from this information, we'd also know that we're going to reject the null. We'd also reject it because 0.75 is in our fail to reject, so 0.75 is in the interval. and that's it.